Presenting on UAS Lidar, on a UAS Lidar pilot project in southeastern Wisconsin. Dick Kleinnman from Ayres. Dick Kleinnman, a professional land surveyor, is a geospatial project manager with Ayres Associates and is actively involved in the geospatial community, serving at the local and state and national level. Dick currently serves as the Wisconsin director for the National Society of Professional Surveyors. He's also the co-chair of the Wisconsin Spatial Reference System 2022 Task Force, and he serves as a member of the TRB AKD 70 Geospatial Data Acquisition Technologies Committee. Dick has 40 years of surveying experience in both the private and public sectors. He obtained his Wisconsin Land Surveyor license in 1985. So thanks, Dick, for being here with us. Look for your presentation and take it away.
All right, cool. I'm gonna have to stop saying how long I've been in the industry. So let me share my screen here. All right, guys should be able to see my start screen there, Nick.
Looks good.
Sweet, thank you. All right, thanks again. As Matt mentioned, it's such an honor to be able to, present for WLIA. Great organization, great people, and the goal is to learn from each other is the way I figure it. So why don't we get going here to just knock her off. Like Nick said, I'm presenting on a UAS pilot project we completed in Southeast Wisconsin. I've got to get my cursor over here. All right, go through the agenda, some introductions, the pilot project background, goals and purposes, go through what I did to get my game plan in order, and some lessons learned and adjustments made. And I'll preface that with a lot of these lessons learned are known by the guys out in the field. And my goal was to, as a project manager and somebody that, helps people understand what they're getting is, that's my goal here, is to kind of share those kind of lessons. And we go through a little bit of data comparison and some final conclusions, and hopefully we have some time for Q&A at the end. So introductions, well, Nick went through it already, but here, there you get my COVID haircut under the hat picture. Actually got to go outside. That's kind of cool. Usually driving a desk, right? This is a little thing about Ayres, and basically I think what differentiates our firm from a lot of others is we're actually a full photogrammetry firm with well, the top there, the licensed Part 107 pilots, and certified people in photogrammetry, certified mapping scientists in LIDAR, GIS, and the big thing is those photogrammetry and LIDAR software seats for teasing that data out of the stuff. Our fleet, Matt kind of went through that, basically some mapping stuff and some inspection drones. Let's get into it. All right, pilot project background. This was my working title, and I know there's a few WisDOT people on the line and they saw this a long time ago already, but yeah, I started out with that realistic expectations for planning and executing UAS Lidar and imagery missions in an urban environment with existing regulatory constraints. That put me to sleep too. So I changed it to balancing data acquisition requirements and regulations. I thought that was better. So did the kid, apparently. So a little history on the project. Get a lot of slides, so I'll be going through these kind of fast. But a lot of you know I came from WisDOT before I started at Ayres, and at that time WisDOT was talking about UAS things, and I know there was a statewide working group active even before 2016. Ayres participated in WisDOT's application to the FAA UAS Integrated Pilot Program in January of 2018. That was the deal where the feds were establishing these test sites across the country. Unfortunately, Wisconsin wasn't chosen on that, but it was an honor to be able to submit with WisDOT. funding, nothing happens without funding, right? So WisDOT received a FHWA stick grant for their UAS statewide program. And before we did this pilot project, the grant monies went towards doing studies and structural inspection, roundabouts, and construction progress before this pilot project happened. So we started discussion a long time ago with Lance Parv at the Southeast region back in January 2020. And here we are over a year later, and wow, what a year, right? Who would have thought I would have been on a job site wearing a mask? And after that, we finally getting the project designed, figure out what it was going to be, and all that stuff took to the point where we finally inked the work order in August of 2020 under our Ayres master contract. And the way it turns out is, you know, it was a stick grant, but basically you got to have somebody who's going to have the project, and it kind of originated in Southeast region. So it turned out to be a Southeast region project. As I said, Lance Parv started it, but it was the journey here was that Lance ended up retiring about the week we got the work order in place. Here's where the beginning of that grant money comes is, and WisDOT's got a really great innovation program that they're working on. It starts at the federal level, and then you see down in the bottom level left that each state has a state transportation innovation council, and then WisDOT has their own innovation committees and teams throughout the department. There's the FHWA grant source. And then the contracting vehicle that we used was Ayres Associates master contract with the photogrammetry unit at WisDOT. At that time, we still did not have our UAS Lidar and metric camera UAS systems. And we were considering it and working on it. But at that time, we used a great partner, ARE, out of New Hampshire, to do the flight acquisitions with their UAS Lidar and imagery systems. And then Ayres was the prime on it. So it's a pilot project, right? You got to take selfies and photo ops. So there's a couple of shots of the Ayres and ARE team together doing social distancing at the time. And you don't see it there, but yeah, we had to wear masks while we were, you know, at the tailgate of the truck going over the details. Go from there. So purpose and goals. This was all kind of put out when we spun the project up. Basically, we wanted to determine if the UAS technology would support various different types of design needs of WisDOT, you know, and could it be done responsibly with a very minimal traffic control under today's regulatory climate. That regulatory climate, the FAA rules flying over people nighttime and stuff is a moving target. It's going in the right direction and opening up some, but it's still going to be quite regulatory, I guess is the way to still think of it. We wanted to test various acquisition and processing workflows and their effect on the safety and the data. Wanted to determine what kind of projects could be done under the current regulations. The focus of this one was ADA curb ramps, but there are so many other projects that this technology could be used on. I wanted to get a good data set for WisDOT to be able to play with and work on. Other thing was we wanted to compare this UAS LiDAR data with a manned helicopter and static LiDAR to kind of see different levels of accuracy, density, and detail. And the biggest thing was, I think, was just to continue to make progress under the current regulations. You can't sit around and wait for the regulations in the perfect time. You got to see, well, what could we do now, right? So the project was kind of unique in the fact that WisDOT had Ayres Associates process the helicopter LiDAR and fixed wing imagery in spring of 2020. And we did their mapping that will actually, I call it the real project, where they're going to be building or rebuilding this road from. So we had that data in place, and we chose 3 intersections as subsets of that data to do this pilot program on. As I said, there was manned helicopter LiDAR, a complete data set over that entire area, and this is a look of it. You can see the kind of detail that you're getting in there. Nice, very dense aerial mapping to work on. On the right, you can kind of see a zoomed in view of the Jackson Drive intersection. And along with that, so we had the first data set, the manned helicopter. But for this pilot project, we decided to acquire static LiDAR using Ayres Trimble SX10. That's a combination total station and a LiDAR scanning unit that sets up right on the project control. You can see there the orange markers right next to a project Fennel control there. And here Zach is actually using the total station mode. He's got the prism there, and he did some actual conventional work there too. So that was done only at Jackson Drive because that was the intersection that they're focusing on ADA curb ramps. And it provided another set to compare the UAS data to. And you'll see why we kind of consider that the gold standard. You know, I don't know that you're going to get any more detail or any more accurate, you know, within reason than going with the high density static LiDAR. You can see the amount of detail in this. What you're looking at is a colorized point cloud from that SX10 scanner. And again, so that's a colored point cloud. That's not a photo, right? You know, and this is where we get into talking about detail. You know, sometimes you regret that you have that much detail. You can see in the processing, I looked at some of the data and I said, well, what happened here, you know? And then I went and grabbed the data, looked at it, and I said, oh, okay, the sidewalk is like a full tenth and a half settled below the curb, you can see there. In the software, QT Modeler struck a little cross section through there to see what that looks like. Here's what that looks like in cross section fashion. Say the grid interval, there's a 1/10 of a foot. So yeah, it's a good 10th hop. And there's a good look at how uniform a point cloud from a static scanner is, how thin that is. It's only about maybe 200 thick sometimes. And you look at like, wow, what happened there on the curb? It got kind of, you know, thin, but like, okay, you know, I think about 75, you know, points is good enough to define that chunk of curb, right? So that's the gold standard we're kind of comparing things to. Back to the game plan, in designing and picking those intersections, I was looking for something, again, right, realistic. Would you fly the entire 2-mile long project with the UAS? Yeah, maybe if it was in a rural area or you didn't have this kind of focus. But instead we kind of looked at like, well, let's look at intersection based. And I picked intersections that weren't necessarily easy, but basically had one cross section or one crossroad to deal with. And then overall, the project kind of covers a variety of different configurations. What was it, 2-lane, rural 2-lane, or yeah, with ditches and woods, some multi-lane intersections with turn lanes. And then down there in the middle, you see the Jackson Drive intersection. The focus was ADA ramps there. So variety of land cover. So again, trying to balance that data acquisition needs with regulations. I had one intersection, I had kind of had my real conservative approach of sacrificial, I call it. Let's do everything we can do to not cross that road with the bird. Basically, You know, it's an intersection, you're gonna have to cross it somewhere. The cyan, the light blue is our mapping limits, and the yellow is the flight path. So what that did is that introduces like 90-degree or even sharper than that turns. And the concern was, well, what does that do to your LiDAR data, your acquisition? Same thing here. This is the imagery flight plan, staying off of the road, flying a grid pattern for that. But on the remaining AOIs, area of interest, we try to use straight lines, consistent flight lines. That's good for aerial sensor platforms, that they're stable and not moving around. The more you're jerking around type thing and turning, the more, think of those hundreds of thousands of LiDAR data points flying around, and you need to be able to locate them. So stable flight line is very good, except for you got to keep in mind not too stable too long, because the IMUs drift over time. But you can see this is the LiDAR flight plan, east-west, and then two to cross to tie the two LiDAR swaths together. And I'll get into the career views later. This was the imagery flight plan for the eastern segment. We went beyond the area just to capture some more data. But again, straight flight lines, avoiding overflight of the road. Again, it was all about minimizing risks. What we did in this case was we utilized for the imagery portion was a UAS that had an onboard airframe parachute that would deploy if there was a problem, and the whole thing would come floating down softly. We were able to do that because ARE has a Part 107 waiver to be able to do that. And that simplified things, I guess less headaches for the imagery portion anyway. So here again was the platforms we flew for this particular project. These were ARE's systems at that time. I'll show you the ones we had later. I actually Matt showed them to you. So we were flying a Phoenix LiDAR system. So like ours is a True View based on a Regal system. This was a Phoenix based on a Regal Bux 1 UAV. LiDAR sensor with a Sentinor STIM 300 IMU. Sounds like something out of Jetsons, right? But it's a high-end, good IMU, good specs on it, and their IMU flight control system there, Novatel. Big thing is we were scanning at 550 kilohertz, so that's 550,000 a second, I believe, as Matt was pointing out. And the airframe carrying it was a DJI Matrice 600. And the one on the right is everybody recognizes the Phantom Pro 4 or Phantom 4 Pro with a 21 megapixel camera and the parachute. So that's what we were flying. And this was our targeting on there, right? All good projects start with good ground control. We GPS the ground control for horizontal 280 epic observations. The 200 series targets were the main control targets. That's the upper left there, the cross, the 2-foot long cross. And we added those little 3-inch squares in there because we knew we had high res imagery for that. The 300 series were just validation points that we withheld from ARE because they were the ones doing the initial calibration to the control, and the Ayres did the processing of the classification and mapping and stuff from that. 400 series was the PIDs, photo identifiable, you see them later. The 500 series was added ones in the static scan intersection to get a little denser stuff. So this was the targeting game plan. You can see, spread your control all around, and you see the red PIDs, the photo identifiable points, were on the outer area to control or help control those imagery missions that went way outside of the mapping limits there. Here was the real core of the pilot project was the Jackson Drive intersection. the cyan mapping limits, and the red was the static LiDAR collect area. You can see the odd ones, the purple ones were those added mini targets to kind of tie the static and the UAS together. This is the easternmost AOI over by Eagle Drive, the pig. It's right next to a Piggly Wiggly. You Wisconsin folks know that, but our New Hampshire folks thought that was pretty good, so it ended up in all the file names. So, game plan. This was a big part of the thing that I wanted to show or share was the logistics, right? Can you do this as, you know, we've all seen the tests out in the rural areas. I'm not taking anything away from them. Those are very needed and necessary tests. But I wanted to see, well, can you really do this in a more congested area type thing? Dealing with upper left there, traffic and pedestrians. Bottom left there, I had, that's my traffic control device, basically. Cross guard style paddle, slow on one side, stop on the other, right? We were trying to keep it simple. We never stopped the Highway 60 traffic. We only used the traffic signal timing for that. Takeoff and landing zones, logistics, you got to find them. The east and west ones, not a big deal, but the center one was very limited in where you could work. Notify the police. Basically, I worked out with them. We were like, well, should we put out a Facebook post and all this? And we're like, nah, maybe not. Both the police and us decided it's probably best just so they know what's going on if they get calls. And we didn't broadcast it because that would have created more logistics. People, you know, stopping and, you know, getting in the way. School right down there, right? As I told you, this project was designed over 8 months, basically. We thought it was going to be a spring flight, then we thought it was going to be a summer flight. But by the time we got the work order in place, it turned out to be the week after Labor Day. And guess what starts that week? School. As I drove up to the job site, I'm seeing parents in minivans all over the place, and I go, no, it's first day of school. But it worked out. We worked on the eastern intersection, and with the virtual school, it went away by 10 o'clock or something like that. And the last thing is a thing you wouldn't think of is during the manned flight in spring, Ayres did the targeting for that. So I was out there watching for ground conditions, and I noticed garbage cans, 95-gallon bins out there, hundreds of them up and down there obscuring the curb lines and stuff like that. So I said, let's try to avoid garbage day. And once you know, we ended up flying on garbage day. So I had to move a few of the carts. So those are all things you got to deal with. Last thing is this is on every UAS flight that you got to watch out for hazards. There were transmission lines to the east. Here's a look at those transmission lines in the manned helicopter data. Not a small obstacle, right? But the good news is we were well west of them. And here was the interesting thing that having that data, a guy could actually go through and use all the resources available to you. Go in that point cloud, boom, do a cross section, tells you exactly how tall those towers are on the left. And those are the wires actually crossing the road that you could see elevation for. This was the other obstruction, radio tower on the village hall there, just west of the intersection. There's a LiDAR picture of it. Clearly you could pick up that small tower and on the right, a cross section of it. So we knew, hey, you better be flying, you know, above 990, you know, 1,000 feet MSL on that area. But again, that was horizontally off to the side. So that all aside, if you don't have all that great data ahead of time, right? You're out there, you've come from a long distance, you pre-planned your flight, but you don't know how tall the trees are, right? So basically, you still need to go out there, take up your little Phantom, raise her up, put the camera horizontal and observe how tall those trees are. And in this case, I believe we did bump up our lowest flight because the pilot and command was a little nervous about that. He said, nah, I want a little more clearance. So he bumped it up. And that's an actual point cloud from the UAS data collect. You can see the congested site wires, light poles, trees, buildings. And here's where I was going to get at the curlicue flight plan, right? This is, again, something the pilots know, right? But as a project manager, if you're not out on these things, you don't think about that. But when you're picking sites, the pilot needs, the first thing they do is they fly around and they excite that IMU and get that thing disturbed. So it's all calibrated and initialized. That's the IMU is what tracks the roll, pitch, and yaw, the position of the UAS and the sensor, right? So it feeds in all that data and you need that to be active. So they fly around there and we picked a site off to the southwest here. But key is that he still had the main in his line of sight. So so your options were kind of limited in this case, but we felt, well, we're in these backyards, nobody's back there, good place to do it. But in order to get there, he had to do a pretty steep takeoff and landing. You can see here to get up to that that level. And on the next screen, you can see, why, right? There's where we were in that parking lot down there. And this UAS data is so dense, colorized. I mean, you can see the pilot there in his orange vest in the middle on the bottom, and his instrument or sensor operator at the tailgate watching the monitor over there. And I'm probably one of those other figures out there. But that's the wires are across the road that he had to miss. So there was a great challenge. And this gets into the takeoff and landing zones. This is the Jackson Drive one where we were very limited to where we could take off and land. And it was a former gas station, right? Rebars in the pavement and God only knows what's buried down there. And basically you got to watch out for that kind of stuff versus, taking off from a farmer's field with no kind of magnetic anomalies out there. It, basically messes up the navigation devices and can create some erratic takeoffs. So things about the actual conducting the flight. So it was like timing those limited street crossings, right? We tried not to cross like during a data collect, but it was okay while you're transiting between swaths, but you still got to cross the road, right? So it requires that the operator is adept at really utilizing their flight management system, what they're running on the iPod, right, or iPad, to control the UAS. You may be stopping, slowing down, or speeding up that UAS. But that's easier in some flight management systems than other. The big thing is sometimes you do that if you want to adjust. That's where I call, we don't at Ayres, we just don't hit the easy button in processing that Matt does. This is what the PICs have to do too. They got to be able to know how to manage their system. If you leave the pre-planned flight plan, you may not be able to go back to it, and you're going to be, hand flying it manually type thing. So knowing it, what your capability is, the last thing you want to find out is like, oh, well, I can't get back onto my thing, and your head's down, you got your head in the screen and not watching, where you're flying. So in setting this all up, I felt it was crucial to, design those flight plans, to only cross one side street that's within visual line of sight, so the pilot and command can adjust, to the traffic. So between him being able to slow down, speed up, or stop, and having one person with a traffic paddle out there was very sufficient in this case. Did I do that on the westernmost one? No, because there's no way one person could have controlled all that turning movement and stuff like that. That's why we had to go to the ultra conservative flight plan on that one. That was here, yep. don't try and stop your main highway, you know, minimize traffic control. You know, everybody's thought, well, I could fly that intersection, right? If we could close it down. Yeah, you can do that once in a while, but you're not going to do that in a high volume intersection. Keep the traffic control simple. Take advantage of those traffic signals. They create gaps in the traffic so you can cross. In this case, stop bars at the traffic signal were way back from the intersection because the geometry of the intersection didn't allow real good truck movement. They had to swing way out, so they moved the stop bar back. And guess what? Made them people stop outside of our flight line. That was a good thing. So safety first, right? You guys do all know that you're actually FAA licensed pilots, right? And you got to have that aviation safety mindset. And you got to be thinking about risk management. You know, in an urban area, you know, the stakes are higher, requires an experienced crew. We had a case on this one where I was a spotter. Behind my back, and there was a manned aircraft flying. He was below 1,000 feet and just cruising right down Highway 60. And I called airplane, and the PIC immediately had to abort the mission. You know, where was this guy coming, going? There was like, there's no airports around there. He's just on a Tuesday stroll, right? It was a nice day. Got to watch. At one point in time, the UAS, that Phantom just ignored his flight plan. PIC had to regain control, switch to manual. Not a big deal. He was prepared for it, but you got to be prepared. This one I mentioned too about erratic takeoff and take quarters because of that magnetic interference. He told me about it after a while. He handled it to the point where I didn't even notice it. So you got to have emergency procedures in place. Practice those emergency procedures, and you should be able to, you know, be proficient at manual flight, just like a manned aviation world, fly the aircraft, right? So let's see, we're getting through this pretty close. These are all the flights we did. Like I said, this was not a production environment. They're not, we've already did that in the spring before. This is a purely experimental process. So I think there's like 11 flights over those 3 intersections. You'll see at different altitudes. Jackson Drive, we flew at both 120 foot and 200 foot to see what was, you know, the difference in the LiDAR data. And County P, we flew at 400 feet because that, with this sensor and that bird, would be probably your sweet spot for a production flight. So we wanted to see the density at the data there. And at that case, yeah, scanning at 550 kilohertz, 12 miles an hour, forget how many meters per second that is. One of them, yeah, the Jackson one, we flew low and slow. Very dense data there. So this one here, so adjustments made. Yeah, this was all about the 90-degree turns and what's that going to do to the data type thing. You'll see on the next thing here, this is where you know, a high-end IMU is crucial. That as you're turning in place almost, right, with a quadcopter or whatever, you can turn in that scan pattern is like a straight line, and it's moving very slow on the inside and very fast on the outside type thing. So the IMU is real critical on that, right? Roll, pitch, and yaw. And then scan rate and the speed of the bird was, you know, can compensate for that too. But here's where that scan rate paid off. I don't know, hopefully you guys can see this. It's hard, it doesn't translate. I had to zoom in just right to the data to be able to see those striations. You can see how they're radially turning in the bottom right. It's the most apparent. So that, you know, there's cross from the other side, right, and stuff like that. But basically, this was a 400 foot AGL flight. You see that 900 or 90-degree turn, 550 scan rate. But the data was still very dense and we get all excited about this data, but you do know we throw out 90% of the data, right, when we make the maps. So 200 scan rate would do just as well. But what I am interested in is, are there any localized small anomalies in a, a 10-foot chunk of curb, something like that. That'd be for further investigation. Yep, there went into that. So I'll cruise through this. Matt already kind of went through the difference between a imagery-based point cloud and a LiDAR-based one. But this was a case where we didn't have our stereo system, our metric camera to fly and do planimetric mapping in a stereo environment. We did it heads up digitizing, just like you would take your ortho photos, your county ortho photos, and draw curb lines over them. That's basically what you have to do if you don't have a stereo environment of imagery, overlapping imagery to work from. So in this case, this is that heads up digitizing, and you see the gaps in the data caused by the trees. And granted, you wouldn't fly in September or leaf on like this for this critical a job, but we took advantage of that to show the warts, right? Let's do a difficult job, not an easy one. There's a just different view, right? There's the gaps, and you notice some of it goes out into the sidewalk. Why the gaps? Again, there's maybe some different slides, but I think they're valuable, and they show that this is a LiDAR derived point cloud with good vegetation penetration. You can see underneath those trees. And know that at the colorized, the road took on a green because it's going through the camera, is looking at the leaves, so it colorized the ground as green. But here's that same area, same view. This is one of the flights we did and made a point cloud out of just the imagery. And you see some pretty significant gaps in that point cloud derived from the imagery only. Here again is a low level view of the LiDAR point cloud, nice and detailed, a lot of density, plenty of data there. But here you look at the gaps in the point cloud derived from the imagery only, the pixel matching. So this is kind of, why we think it's important to have that capability is this, combining the UAS stereo imagery and LiDAR workflow, allows each data set to verify the other. You work in the environment, you bring these together, and you can do something in the LiDAR and then verify it in the stereo compilation area, right? You can float your little puck up and down there and test the LiDAR, or the LiDAR tests the imagery. So the combination of the two produces the most complete and accurate DTM and planimetric. That's why Ayres was already on track, thinking about this and investigating those kinds of systems when we started this project. And there's our new birds, got to advertise those. And last but not least, let's compare the data. So basically, this is somebody asked, how do you do that? Matt uses his LiDAR processing software, TerraScan, runs a vertical accuracy report. I wish I should have included one of them. It's basically just the difference between the ground survey point that's at 300 series validation points. So there was, I think, like 13 points all told on this job that we tested against the point cloud. And we stopped there at the point cloud, but because the idea was to test, is UAS LiDAR suitable? Most of you know, if you've made a 3D surface from raw data, you can, you use a part of your air budget by doing bad brake lines or no brake lines and stuff. We really wanted to just test the point cloud. And then compared it against the static LiDAR and the manned helicopter. And here were our results. And granted, take this with a grain of salt. We didn't have like a great abundance of test points, but I think it was enough to tell the story. Remember back about these accuracies and that slide that shows that the sidewalk settled 15 hunters. I mean, every year that sidewalk goes up and down, right? So you're looking at here, the static scanning tested the 7,000th root mean square Z. So if you surveyors in the crowd want to deal with 95, multiply that by 1.96 or double it, So can you deal with like 14 thousandths error? I think so. The average of all the UAS Lidar flights was 17 thousandths RMSE. That was the 400 foot, the 200, the 120 altogether. But they were all in that neighborhood within 5 thousandths of that 17 thousandths. And the manned helicopter flight, we use those same test points for this one against that helicopter data that was acquired in spring versus fall, but 43 thousandths root mean square error. Very good data to be able to build roads and design stuff from. So in conclusion, right, the big thing is it possible to work in this environment and get a successful project? I believe you can produce, accurate data on difficult sites like this under the current regulations. If there's always a caveat, right? You've got accurate ground control, like Matt said, you got to start with ground control that is an order better than what you're collecting. The operator knows their system well. He's comfortable to work in that, or she in that environment. You integrate safety measures. You adjust for the site conditions. You just can't plow ahead with your pre-planned concept of what you're going to do. You have the expertise to merge data. Maybe for this one, for what you want to do is you merge the static stuff with the UAS and in the big picture for the manned, right? There's different things you can do. And I think you need to have at your disposable professional grade airframes, the UAS itself or the drone itself, professional grade IMUs, sensors, great difference in the variety of LiDAR sensors, from ones that are made for controlling autonomous vehicles to serious surveying tools like these. Flight management systems vary greatly. You don't have to use the one that comes with your equipment. Sometimes there's a better one. Photogrammetric software suites, tested workflows, and knowledgeable and certified staff for processing the data. So I think it's possible. It's just not, it's may not be easy. Let's go that way. And I think we just got hit on right about time, not much time there, but if there's any questions, I'd be willing to entertain those.
Yeah, thanks, Dick. That was a great presentation. If anybody has any questions for Dick, please feel free to put them in the chat and he can try to answer those during this next presentation. But thanks again, Dick. I appreciate the presentation. I think it was really interesting how you kind of went through the whole project management, how you set up a UAS project, and there's certain things that you don't think about, like garbage cans on the sidewalk or kids going to school, and how that can, play into the effect of what you're, it took months of planning and all of a sudden, oh, we didn't realize this was going to happen. But that was a great presentation.
Yeah, hopefully not all of them are months of planning, but
yeah.
But yeah, think about it. Thanks, Nick.
Yeah,
very much.
I've never thought about garbage cans so much.
I will now, though. That's going to be in the back of my mind. But thanks again, Dick.